So I started to have these ideas about ways I could make this even cooler than what it is. And one way I thought is about the idea of needing to program what the multiplier is by this dip switch here. And so I was thinking about it, and I realized that the circuit that I have only is able to count up to 7 bits, or two 4-bit binary words. So what that means is that I can only multiply by 9. I can't multiply by 10. That would cost me more bits than what I have available. And so what that means is that the 0 on the rotary dial is essentially useless. I can't do anything because 0 times whatever would be 0, and 0 means no lights light up. That's not very interesting. So I thought, well, what if the 0 could do something? Instead of just being a wasted number, what if the 0 put you into a programming mode, and then the next digit that you dial would be the multiplier that would be stored somewhere. And to store it, you'd have to have some kind of a RAM. In electronics, that RAM is called a latch. And these two chips right here are latches. They're registry latches. And so I thought, well, that'd be kind of cool. Let's see if we can make that. And so right now, what you see is the circuit's indicating that there's a 1 stored in the memory latch. And that means we're going to have a 1 as a multiplier. So if we dial, say, 1 times 1, we're going to have 1. There we go. And if we dial 2 times 1, we'll get the 2 to light up, and it's going to count down. Okay. If we dial, say, 4 times 1, we get the 4-bit to light up, and then it's going to count down 3, 2, 1. All right. Well, that's cool. So let's see what happens if we dial a 0. So that's going to put us in programming mode. So basically what I've had to do is switch from BCD input to binary input. So now the counters actually count from 1 all the way to 10 instead of 1 to 9. So now what we're doing is we're capturing when we have a 10 here. And now the circuit's basically in programming mode, which means the next digit that I dial, let's say I dial a 2, is going to be captured, put into the registry, and stored as the multiplier. So now if we dial a 1, 1 times 2 is 2, so we'll get the 2 to light up, and it counts down. 2 times 2, if I dial a 2, would be 4, so the 4 lights up and counts down. Let's go 4. 4 times 2 is going to be 8, so we get the 8 to light up, and then it counts down. So that's really cool. It's actually working. We're able to store the multiplier and access it via a programming mode from the dial. And that's done completely without any kind of coding or programming chips. This is all discrete logic. And so to accomplish that, I was thinking, well, what would that actually look like? And the first thing I had to do was switch from BCD to binary, because in BCD there is no 10. All right, so if I dialed a 0, I would get a 0, and 0 means 0, 0, 0, 0. There's no input to check for. But by switching to binary mode on the counter chip, which is right up here, now the counter is counting in binary, and so we can monitor for a 10, which is 1, 0, 1, 0. All right, so when I dialed the programming mode, you saw that the 1, 0, 1, 0 lit up, and now I can actually monitor for that. So then I thought, well, what I need to capture that value, right? There's no like variables here. This isn't programming. This is, electrons. And so we actually have 2 memory registries. The first one captures are you in programming mode, and then the second one captures the multiplier that you dialed, all right? And so what we'd have to do then is latch that 1, 0, 1, 0 into the first memory, and then get a finished pulse. In other words, the system isn't dialing anymore. We're done operating. And then what we'd have to do after that is enable the secondary memory latch to put it into a mode where it can receive the input. All right. And what we've done there then is when we enable the programming mode 1, 0, 1, 0, we have 2 wires that go to an AND gate. And it says if this one and this one, then we know that we're in a programming mode, and it turns on the registry enable on this chip. All right, so then I haven't done this yet, but if you're in programming mode, you probably don't want it over here counting whatever digit you dialed. So we have to disable the output, just disable the output when you're in programming mode. I still have to do that. So then you dial the next digit and it captures that. And we get the finished pulse for that, and we store that finished pulse into the memory latch here. Then it got a little bit tricky because once this memory is stored, now you need to say, well, if we have a stored digit here and we were in programming mode, now you need to disable the write to this registry. In other words, save that digit into that registry. So I had to do some interesting stuff with the clock here to determine, was I in programming mode? Did I get a finished clock pulse? Okay, then disable the write on this guy. In other words, save the number. I still will probably create an octal bus here, which will allow the output to be a little bit more interesting when you're in programming mode. And then we would turn that output back on after that. So I just have to do these last two tasks here. But that's really cool. We actually have a programmable circuit with no programming. This is all moving electrons, and that's super rad in my book.